Hello everyone, so today we'll be talking about light waves. Before we can really get into optics and all of these lenses and reflection, refraction, we have to see what is light. We know it's a wave, but what are its characteristics? Okay, so firstly, similar to sound, light is often depicted as a wave with all the same features as something like a sine wave, for example. Has the same wavelength, frequency, and amplitude that you would see in any other sine, cosine, whatever wave. Some specific vocabulary that probably isn't used very much in sine waves and cosine waves is this idea of nodes and antinodes. So we know a crest is this peak over here on the top, and a trough is this peak over here on the bottom. But these together have a special name called antinodes, and it's any kind of peak. So right here at the top, crest or trough, all of these are known as antinodes. Whereas a node is all of these locations where on the y-axis it's equal to 0, where it crosses the line, right? You can see here, 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 right? And otherwise, it's the same amplitude wavelength. Nodes and antinodes may be important to know just for the sake of vocabulary, because sometimes in a question or in a passage or in an answer choice, they'll specifically use this vocabulary rather than crest or trough to explain something. Okay, so it is good to know that. Next, we want to talk about what are the important quantities for a light wave. Firstly, we want to talk about velocity. As we know with everything else, velocity is usually represented by this letter v. However, with speed of light, it's a little bit different, because the speed of light in a vacuum is such an important quantity. It's actually represented by this other letter, sometimes called c, right? And that represents the speed of light in a vacuum specifically. And that's really important because we're going to be talking about speeds in other mediums, which are not 3 times 10 to the 8th, which is the speed of light in a vacuum. But in other mediums like glass or water, speed of light is different, and we'll talk about that later today. But in air or in vacuum, it would be usually written as c, although v could also work for velocity. Next is frequency, which has the letter f, and it has units of hertz or 1 per second. Usually when we think of frequency and hertz, we usually think of sound waves, because obviously sound waves have different frequencies, which kind of make the sound different. And that's how we know them, right? High pitch, low pitch. That's what we know as hertz. But light waves also have a frequency, and it's a key aspect of all waves. And they can also use this unit hertz, but more commonly is used 1 over seconds. That's the more basic, I guess, unit system, the more standard unit system for frequency. Lastly, we have wavelength, which has the symbol lambda with units meters. Okay, and this is very self-explanatory. It's just the length of one full wave or one full rotation of the wave. All three of these quantities are very closely related throughout the equation v equals f lambda. This is an important equation just to help get different values from different information, depending on what the question is asking for. One thing that I always say about physics specifically is to know the units, because let's say on the test day you don't remember this equation for some reason and you forget it and you get a question about it. Well, one thing you can do is you know that the units of velocity are meters per second, the units of frequency are 1 per second, and the units of wavelength are m. So meters per second equals 1 over second, which is for frequency, multiplied by meters, right? If you look, actually, what would happen is that when you multiply these two values, you would also get units of meters per second, just like you would with velocity. So using just these three values, these three numbers, if you know the units, you can find the equation. If you say, don't remember, is it velocity equals frequency times wavelength? Is it wavelength equals velocity times frequency? You don't remember exactly what the order is or something like that. Or for the more complicated equations, if you don't remember them, this is something that you can use on test day as a backup. So I always say pay attention to units. Next, we'll be talking about electromagnetic spectrum, and this graph, I'm sure many of you have seen this before. It should look very familiar, but I don't want to go over it, and I think it is important to memorize at least the key aspects of this graph. First thing I want you to notice, first the order, going from left to right of all of these types of waves. So radio and microwaves, very low energy, very safe, I guess, especially radio waves are very safe. Infrared it has red in the name, so it's relatively low energy, very similar to red, like the visible color red, but it does encompass, actually, if you see, a lot more of the wavelengths, right? Then there's visible light, which actually is really small part, and it covers all of the rainbow colors from red to purple or violet. Then after that, you have ultraviolet rays, which I'm sure you know from just the sun. Those have a lot of energy and they can be actually kind of harmful. And then obviously X-rays and gamma rays have a lot of energy and are very harmful. So knowing the order from left to right is pretty helpful. And next thing I want you to focus on is the wavelengths and frequencies going from left to right. If you notice, wavelength on the left side here is big, it's about 1,000, versus all the way on the right here, gamma rays, it's like 10 to the negative 13th is like in the nano or in the pico meters. It's really small. So wavelength, as you go higher up in energy, you go lower in wavelength. What this means is that wavelength and energy are inversely proportional. As one goes up, the other goes down. If one's high, the other is low, right? Very important. Frequency, on the other hand, is inversely proportional to wavelength, meaning it is proportional to energy. You see here the frequency here starts at about 1 million, goes up to this really big number, 10 to the 22nd, as you go from left to right. So frequency and energy are proportional. Wavelength and energy are inversely proportional. Okay. And then you have the visible spectrum magnified here, and it goes from red to violet. And if you remember the colors of the rainbow, Roy G. Biv, it's in actually the exact same order, starting at red, orange, yellow, green, blue, indigo, violet. Okay, Roy G. Biv, from left to right, from lowest to highest energy. And remember that infrared is less energy than visible light. Infrared has red in the name, so it's very close to red. Ultraviolet has a lot of energy. It's very close to violet. It has violet in the name, so it's very close to violet in the spectrum. So red is closer to the low energy side, to infrared. Violet is close to ultraviolet, high energy side, and then it's just Roy G. Biv for the middle. Okay. Visible light ranges from 750 to 380 nanometers in length. You can see it's actually really, really small section here. I think you might want to know the range of visible light. You don't have to know I don't think you have to really know the specific range of like where's red light, what range is green light. They'll usually tell you either in the passage or the question, but you should know the general range of all visible light. Again, remember low wavelength means higher energy, so 380 nanometers is violet, while 750 is red. The order is the same as in a rainbow, Roy G. Biv, from lowest to highest energy. Okay. As we mentioned, wavelength and energy are inversely proportional. They're very closely related. This is because the equation for energy of a photon or a light particle, because I'm not covering this in depth because I don't think it's extremely high yield, but light is both a wave and a particle, or can act as both a wave and a particle. Photon is a particle version, a particle way to say light, essentially. The energy of a photon is E equals hc over lambda. E is energy of the photon. Obviously, all energies are in joules always as units. Planck's constant, which you don't have to memorize, is h. You don't have to know this number. I'm just putting it on the screen. If they ever want you to use it, they'll put it in the question with the units as well of joules times seconds. Then you have the speed of light, which I mentioned is c, 3 times 10 to the 8th meters per second. And then lambda is wavelength in meters, right? And it's over lambda. And again, focus on the units. So energy is always joules. Planck's constant, like I said, they'll usually give it to you. Joules times seconds, so you don't have to memorize it. Speed of light, you know, speed is always meters per second. And all over, so I'll just do 1 over wavelength, which is 1 over meters, right? Again, looking at the units, seconds cancel out, meters cancel out. All you're left with is joules equals joules. And that's very simple to find the equation if you ever forget it. Okay. All right, so let's do a quick question. If yellow light has a wavelength of 570 nanometers, which wave has a higher frequency than yellow light? Okay, so the answer is violet. Like I mentioned, frequency and energy are proportional since wavelength and energy are inversely. So frequency, energy, proportional. So saying which has a higher frequency is the same thing as saying which has higher energy than yellow. Again, if you look at Roy G. Viv, like that. Yellow is right here. Orange and red are to the left, so they are out. They're actually lower energy and lower frequency as a result. And infrared is even further left than red, so it's also out. Whereas violet is to the right, so it is the correct answer. You can also kind of figure it out based on just eliminating the other answer choices. So like red, orange, and infrared are all 3 to the left, whereas violet's the only one to the right. Which of these answers is not like the other? So violet. And that will be the correct answer since there can be multiple correct answers, right? That would be an easier way to do this, but if you just want to do it the way I did, where you write it out, put in the IR spectrum, and then figure it out that way, that also is good. Okay, so I hope this was helpful, and now we're moving on to reflection and refraction.